Okay, this is my chemistry room write-up number 2, take 25. Okay, so instead of writing an essay, I'm going to be doing a video presentation. I will be using paper, pen and paper for diagrams to write out equations and electron configuration and Lewis dot structures. I'm wearing this hat because I can. It's a free country, and this is my house. Let's get started. Okay. Number 1. Atoms are always going to have some kind of electrical charge. There are 2 types of charges, which are positive charge in the form of protons and negative charge is in the form of electrons. These will get neutralized inside the atom because if there's 2 of them and they're an equal amount, opposite charges will cancel each other out. Imagine like this. Proton and electron, right? Proton is going to be +1, electron is going to be -1. If you these 2 together equal 0 because it's adding with negative numbers. Okay, when 2 or more atoms are involved in a reaction, they form an ionic bond, where the atoms turn into ions and possess either a positive or negative charge. One example of this would be 2 sodium atoms and 2 chlorine atoms forming table salt, or sodium chloride. Before the reaction, sodium has 11 protons and 11 electrons in each atom. This is canceling out the charges inside the atom. It is the same with chlorine, 17 protons and 17 electrons in each atom. But for the sake of simplicity, I'm going to use only 1 sodium and 1 chlorine atom. The reaction will go as follows. Alright, first, the chlorine will take sodium's only valence electron, filling chlorine's valence shell. Now, since sodium's valence shell is empty, it moves its valence shell up to the previous shell, filling its valence shell. Since chlorine now has 1 more electron than proton, with 18 electrons and 17 protons, it gets a negative charge of -1 and becomes an anion. Anions are negative, cations are positive, because cats have paws. Still, I get it, but I don't like it. Since sodium now has 1 less electron than proton, with 10 electrons and 9 electrons, it has a positive charge of +1 and becomes a cation. Positive. After this electron giveaway by sodium and chlorine are attracted to each other and form an ionic bond, as opposite charges are attracted to each other. Because one of chlorine is going to be negative, but then sodium is going to be positive, so they go together perfectly, and it's going to be very neutral and stable. Here is how the reaction is going to go. It will look like this equation: 2Na plus Cl2. It turns into 2Na plus Cl2, which equals 2Na. It's going to look like this. This is the actual outcome is right here because I didn't have enough room to write out the entire thing. It's quite long and don't want to write too small. So the 2Na is going to be standing for the sodium, 2 sodium, and the Cl is for chlorine. They're going to form together to have 2 sodium and 1 chlorine as a bond, as sodium chloride, aka salt that you use on food. That's how the reaction is going to go. When talking about energy being used in a reaction, as sodium reacts with chlorine, chlorine takes sodium's electron, but that requires energy, and in doing so, uses energy, which is going to make it become warm in the process. Sodium just reacts violently, not only with chlorine, but any of the halogens, which takes energy, making it become hot. The structure of atoms in terms of electrical charges, the more the attraction between two or more atoms, the closer they will be to each other. And how it is affected by other atoms / molecules. Sodium and chlorine become a cation, positive, and an anion, negative. Respectively, after the reaction has occurred and they have turned into ions, since they have opposite electrical charges, they will be attracted to each other and form a strong bond. But their bond can be broken by another atom that has a charge and attracts one of the atoms in the bond, breaking it. Now, I was a little confused at first when we were talking about breaking apart atoms. When you break apart an atom, it's not like this is what I think of when I say breaking. Breaking apart is, for example, if I take this pocket knife and I stab through this paper and break apart the fibers, holding each individual other fiber in this paper. That's why I say breaking apart. But with atoms, it's more about stealing. For example, you could have the sodium chloride, they're bonded together, they form a strong bond, but then another atom will take away one of the sodium, thus breaking the bond. Which is very different than what I originally thought about how that is something I learned. Did a great job at teaching me. Now, each bond has its own properties. When comparing the charges in an ionic bond, similar to this, like this, to another bond, like a network covalent bond in diamond. Ooh, diamonds are forever. The ionic bond is able to sustain high temperatures, though not as high temperatures that the network covalent bond can take, due to the electrical charge being high between the atoms. But ionic bonds are somewhat fragile and are also soluble in water. Because the atoms in a water molecule have a charge, and when the sodium chloride is put in the water, it dissolves and the water molecules break the bond of ions by pulling the ions with their charge. Network covalent bonds, the reason why diamond is considered probably the toughest material, so you don't want it to really, it's very hard to break. The only way you can scratch a diamond is with another diamond. Now, another example of something that is very, very strong, which is a network covalent bond, not as in physical strength and tensile strength, but it won't melt, is silicon. We use silicon on electronics because they have very, very high melting point, but network covalent bonds do not conduct electricity, which is perfect. For example, my computer is right next to me, right there, and the thing is, if that motherboard was made out of some form of rubber, it wouldn't conduct electricity, but it would most likely light on fire or melt. Most likely melt, which is not good. That's why network covalent bonds are great, like silicon, are great for electronics. Could you make it out of diamond? Possibly. Good idea? Absolutely not. To cut a diamond into something like that, it's just not logical. Now, a phase change in a molecule is partly based on the electrical charge between atoms. An example we talked about previously is salt dissolving in water. I just talked about that. Salt can sustain high temperatures. So if I had it under a candle, it probably wouldn't melt. But when I put it in water, it's going to dissolve, and the bond between the sodium and the chlorine is going to break. Another example that is of a different bond would be lauric acid as a solid, which is a molecular covalent bond. Molecular covalent bonds are fragile because the electrical forces between the atoms are pretty weak in comparison, and so they melt very easily, or they can evaporate. Because molecular covalent bonds tend to be liquids or gases most of the time, they will, that's why they will evaporate. They also dissolve very, very easily. Now, sorry, cough. Sorry. Back on topic. Okay. They will melt very easily or evaporate because molecular covalent bonds tend to be liquids or gases most of the time. They also dissolve very easily, as the water molecules can easily attract the atoms in the molecular covalent bonds. Here under is the phase change of lauric acid into a liquid. Okay, so for melting, right? I could have a solid lauric acid, and it will melt at 43.2 degrees Celsius. And then at 43.2 degrees Celsius, it could also freeze past that. So it can melt into a liquid, or it can freeze into a solid. When two objects come in, lauric acid, by the way, in solid form looks like a white powder. It's kind of white powdery. It's not as fine. Like, it's not as fine as It's a little gritty. It's not as fine as baking soda. I'd say more comparison to sugar. Like a mix between powdered sugar and just normal sugar. I don't know. When two objects come into contact with each other, there is some amount of static electricity that is built up. Static electricity is where electrons and atoms leave the atoms when you rub. For example, a balloon against our clothes which gives the balloon surface a negative charge as the gained electrons in our clothes so the balloon's going to get is going to gain electrons, and our clothes are going to get a positive charge since they lost electrons. When this balloon charged with electrons is put near running water, for example, when you turn on the tap water in the sink and put the balloon near it, not touching the water with it, the balloon is going to pull the water towards it. This is because the balloon's negative charges pull on the positive charge of the water. It pulls on the hydrogen atoms in water, H2O, 2 hydrogen, 1 oxygen. Because the hydrogen have a positive charge, as they lose their electrons to the oxygen atom. Now, balloons, when you rub against, for example, if I rub against my hair or like a wool sweater a lot, then it's going to gain the electrons, and so it's going to have a charge, and that electrical charge can be discharged. Like, I could zap someone, like my little brother, after rubbing a balloon a lot on myself, on my clothes. Bonding. Alright, this is my second content standard. Bonding is where two or more atoms react and form a pact about sharing electrons. It is where atoms form a chemical bond during a reaction with energy. A theory that relates to the destruction of bonds in a molecule is as the amount of energy applied to a bond increases, the chance that the bond is going to break is also increased. So the more likely the bond is break, in my theory, it has a correlation with the more energy that is applied to the bond. The reason for this is because since bonds are made using energy, they will require energy to be broken. A weaker bond, like a molecular covalent bond, is easier to break, as it doesn't require much energy to break a bond that weak. A network covalent bond, on the other hand, needs a lot of energy to be broken, as these bonds are made to share electrons evenly, making them near impossible to break. Diamond is a good example of a network covalent bond. An example of a strong bond that requires a lot of energy to be broken is diamond. Diamond is the hardest known natural substance. It's nearly impossible to break. But the reason why diamonds are nearly impossible to break is because the carbon bonds in diamond are so strong that they need lots of energy to be broken. The carbon atoms are sharing electrons of the other atom, making the bond weaker. Another theory that relates to the formation of bonds is opposites attract. Opposite electrical forces are always attracted to each other. Positive and negative charges are always attracted to each other because of the opposite forces pulling at each other. It's like that song, Opposites Attract. She makes the bed and he steals the covers. Oh, sorry, I'll have to ask. Just thought of it because you were talking about it. Alright, so during the one example is going to be table salt. Now, during this reaction, sodium is going to give up its electron, making it a positive ion. Cation. Pause. Meanwhile, chlorine takes the electron sodium is going to give up, becoming a negative ion, which is known as an anion. They then get attracted to each other due to the ions comprising of the opposite electric forces and form an ionic bond. When a set of atoms is compared to a molecule with the same atoms, the molecule always has more energy. That is because the bond makes the molecule stronger, where the atoms are individual and weaker than a molecule that has atoms that are bonded. Okay, let's talk about a third thing. Alright, marketing. How did we market our escape room? We put up flyers. We put many flyers up at Lake Hills Library. I live in Redmond, so I went to King County Library. I got a bunch of my friends who go to Lake Washington High School to get some over there, some at Interlake. So one thing I really wanted to target was high school students that take chemistry. And I know a lot of people who don't enjoy chemistry, but I also know a bunch of people who do really enjoy it a lot. Also, of course, one key marketing plan is we are going to target our parents. Now, our parents have a moral obligation to come and see our work and see how pretend to be how proud they are about what we do. So we got a lot of parents of our group members to go, which was about maybe 1/3 of our customers. We had a lot of customers though, an exceptional amount, much more than expected. Now, our charity was the Wounded Warrior Project. So we wanted to also appeal to people who supported our veterans overseas, people who are also recovering from the military, or people who were enlisted and then were discharged. So then they need money to survive. The military doesn't always have a great pension or severance package. So we were going to we went to places such as U.S. Army Enlisting Center. I went to there. It's next to the Highland Community Center. I put up some signs there, and they totally supported it, and they said that they would tell some people. So not sure exactly how many people got sent our way because of that, but it could have helped. We were also targeting people who have members enlisted in the U.S. military, family members, so then people might enjoy that. And one thing that I think helps is that we decided to make it so there is no required donation. You can donate as much as you like, or you can donate as little as you like. If you want, you can just come in for free. We recommend a donation to help our soldiers overseas, but it is not necessary. And we also targeted college students. I went to University of Washington and put up a few flyers in the student lunch cafeteria area on the forum board. I also one of our group members went to Bellevue College. Libraries was a great place to do because they always support it. Community center in Redmond was also a good idea. That was our marketing plan, and that is all I have for this escape room write-up too. Now, I've gone over the 2 content standards, and I hope you enjoyed my presentation today. I am ready to prove on our final my learning. Alright, thank you for watching.